The Being an Engineer podcast is a repository for industry knowledge and a tool through which engineers learn about and connect with relevant companies, technologies, people, resources, and opportunities. Enjoy the show.
Hello everyone, welcome to the Being an Engineer podcast. I'm your co-host, Rafael Testai. Today we got a special guest. He's a principal engineer at Mayo Clinic. His name is Steve Corner. And one of our previous guests, Sean McGilligut, who was the section head of medical device research and development at the Mayo Clinic. So that's our previous guest, Sean. Sean mentioned Steve Corner, our current guest today, as his go-to person for creative design work at the Mayo Clinic. And Steve has been working at the Mayo Clinic for 20 years. He's also the chair of documentation standards work group. He figures out how to document SolidWorks designs. And Steve is a mechanical engineer with a PE license. So Steve, welcome to the show.
Well, thank you for having me.
Well, first and foremost, why don't you tell us, how did you decide to be an engineer? What was the story behind that?
I don't know if we want to spend the whole time talking about that, but I've always enjoyed science. I mean, through high school and whatnot. I come from a family, though, of non-scientific people. My mom's a kind of art major, and my father was a journalist. So not a lot of science going on in our household, but I still liked it, and I had a certain affinity for mechanical things and taking things apart, and that kind of, I always thought I would be an engineer growing up, in high school at least, and then I got to college and the math got really hard, and I kind of fell in love with geology. So my first degree is in geology. From Michigan State. Then I couldn't get a job and kind of moved out to Colorado, was a ski bum for a couple of years, and then riding the chairlift, a guy told me, you really can't do this your whole life. And I kind of agreed with him, and I thought, well, I always wanted to be an engineer. So I had residency in Colorado, so I applied at the University of Colorado to go to their engineering school, and 2 years later, I was an engineer. So that's kind of how it happened.
So 2 years later, did I hear that correctly?
Yeah. So a lot of my basic stuff carried over from my first degree. So I was able to use that for all my core stuff, and even the math and everything. The geology degree gave me that. It gave me, a lot of basic science, physics, and so that all transferred. So it was actually 5 semesters. So I graduated in the winter, 2.5 years, if you will, after I started.
That's amazing. What a coincidence. So my first bachelor's degree was in molecular biology and genetics, and I went out in the field, but then I came back a couple years ago to get my second bachelor's degree in mechanical engineering. And basically, only 1 semester worth of credits transferred over. I'm basically having to redo another bachelor's degree, 3.5 years of school, all over from scratch. And I'm already a year and a half in to the program. But I'm glad that it worked out really good for you, because you only had to do 2 years when you switch your career.
Yeah, I remember it being kind of a deal to go through, but I had to write all these things about why this class substituted for this class, and it was even more difficult because Michigan State was on trimesters and University of Colorado was semesters. So I had to create these, explanations of equivalence, and I guess that was my first foray into this whole, trying to document things and convince people of things. So it did work out. It worked out, and then at Colorado, I was only taking engineering classes pretty much. So it was very efficient at that point. And fortunate for me, because I was pretty much on my own dime at that point.
So that's a perfect segue onto the next topic. As we said in the bio, you're the chair of Documentation Standards Work Group, and you figure out how to document SolidWorks designs. So take us from a very basic standpoint of understanding. If no one has ever heard of what does document SolidWorks designs mean, if you could explain what that means first, very simple, and then talk about it, what you do in regards to that at Mayo Clinic.
Well, I mean, traditionally it means creating drawings, two-dimensional representations of a three-dimensional part, and we abide by a standard. It's ANSI Y14.5. It's pretty ubiquitous in the in mechanical engineering world. That calls out all the different things you can and cannot do, how you're supposed to present things. So typically, a typical part will be presented in three dimensions or three views, front, top, and side, and then any additional views that need to be done. So that's what, and then assemblies are similarly done on a 2D piece of paper. It's now all virtual or PDFs, but you create these 2D drawings of your 3D part, and that's how it's done. That's how it's mostly done. That's how it's it's basically just a hold, very similar to how it was done when I first started in engineering, back in the mid '80s, to create paper drawings, and so that's primarily what we do. We're a medical institution. We don't make medical devices per se, but we create medical device designs. So we have to abide by certain standards with regards to that, and so we do create drawings of our designs. But I see a change, kind of a sea change going on, and it's been going on for quite a number of years now. But I think it's reaching kind of a head that we're going to stop creating these 2D representations, and we're going to go to what they call model-based definition, or directly working off the models. And we do that. It's almost like our 2D drawings are an afterthought, or something we do for posterity, but not really used. When I create a model of a part, I either send it to a 3D printer, where it does not ever get converted into any kind of 2D representation, or I send it to a machinist who, using their numerically controlled machining equipment, creates toolpaths and whatnot based off of the model. So the model is used exclusively, and the drawings are used not at all. And so why are we doing that? So I think that's going to be a big change in the way we do things, and it already has. We've implemented some kind of I don't know what you call it, kludgy ways of getting away from actually doing detailed 2D drawings of parts. So that's where we are with it.
No, beautiful. So model-based definition, is that what it's called?
Yes. So that's there's MBD for short. It's if you Google it, you'll find a whole bunch of stuff about it. It's basically working off the model. So there's I think your some of your previous guests talk a lot about design intent, and a lot of times when we're making models, if we know we're going to do a drawing, we just kind of haphazardly put it together however way we want, and then we convey the design intent in the drawing. That being like hole patterns being dimensioned off of each other so that they stay together, that kind of thing. But if you wanted to do that in a model-based definition environment, you would need to convey that design intent when you're actually creating the part, which I think is actually the best way to do it anyway. But so then that model is then used by the machinist or by the injection molding house or whoever to create the model, and that's or to create the part, and that's just a very clean. There's less chance of errors. There's all these different reasons for why MBD is better, my biggest thing is that it's better because it's less work. And I am always trying to reduce the amount of work that I do.
I understand. Yeah. Okay. So, yeah, go ahead, please.
Oh, and I just saying we are, if you, like a lot of people maybe listening are you're an engineer, you're working, we have these great resources now, like these outside prototyping houses that make parts for you, either 3D printed or injection molded, and they don't want your drawings. They want your models, and so you're basically de facto working in an MBD environment at that point. You're sending them your model, they're quoting it, they're making your parts for you, and there's some blanket tolerance that they're giving you, and hopefully that's okay. If it's not, then maybe you do need to document it a little better. But that's kind of where we are. We're sending stuff internally and externally without drawings, and that's, and when I say we, I think I'm talking about engineering as a whole.
Understood. So, couple things I'm going to mention here for our audience in case you're listening to this driving. I know what model-based definition is. And I also pulled up an image on Google. I'm going to give you a quick visual. Just imagine your CAD SolidWorks model, but with a bunch of arrows, if you will, pointing to it and pointing at like fillets and different dimensions in the model, and they're calling out the numbers that assign basically the geometries and the values. How would you describe it so we get people a visual of what that looks like?
Yeah, so that's kind of what it looks like if you were to look at it. But the machines that are actually creating the tool paths and whatnot don't see all those numbers. They just see the actual geometry. So yeah, so you create to make it human readable. We add these dimensions, and the software SolidWorks has a MBD package. I believe the Parametric Technology has theirs, ProE stuff. So it's all the big ones have these packages built in where you can take your model and add these. They're called annotations. So you create annotation views of different aspects of the design, and you save those. And then when the person is reviewing the design, they can bring up those annotation views, virtually, and see the 3D part that they're attached to, and manipulate the model, manipulate the orientation for views and whatnot. And that's what I see as being the future of CAD, and not reviewing, a 2D piece of paper or a representation of a piece of paper on the computer.
I think a sentence that you said before we actually started recording the podcast, as we were warming up, you mentioned that documentation in mechanical engineering has been changing or is changing for the second time in your career. So the first time, I guess, was from the paper and pen to CAD.
Yeah, so when I first started, in high school in the 70s, it was all paper and pencil and pen, and we created literal blueprints, where you used ammonia to develop the paper, and it was crazy. And then when I started engineering, it was kind of a mixed bag. People were using computers, but not fully. So there were still drafting tables around, and you draw a sketch of your design, and you take it to a designer, and he or she would convert that into a drawing, a big giant D-size piece of paper drawing, and that's how it was. And you see pictures of like Ford Motor Company or Boeing, and it was just these giant rooms of drafting tables, and so that's how it started. And then I saw pretty early on AutoCAD was the big thing, and we're doing all of our designs in AutoCAD, and but still printing them out in paper, and we had plotters, big plotter things, and that's kind of how it went. And it's pretty much gone that way since. There've been certainly improvements. We're not actually using physical pieces of paper anymore, but the whole 2D representation has stayed the same. And so now this change is from getting rid of that 2D representation and going to a purely 3D representation. You'd definitely have to have a computer or some way to view it, if for a human being to see it. But yeah, the whole idea of the 2D drawing, I see that going away.
When you mentioned that, there's this meme floating around, like a picture that's funny, a meme floating around the internet that says how it started and how it's going. And when you said how it started, I mentioned a whole room full of drafting and papers, and how it's going. Now we have MBD. Pretty cool. So my next follow-up question, I have to introduce who we are at Pipeline, that we host the show. And then I'm going to follow it up with how this relates to what we do at Pipeline. So the Being an Engineer podcast is brought to you by Pipeline Design and Engineering. And Pipeline, the company that I work at, partners with medical device and other engineering teams who need turnkey equipment such as cycle test machines, custom test fixtures, automation equipment, assembly jigs, inspection stations, and more. You can find us on the web at teampipeline.us. So here at Pipeline, we have very big medical device companies that we've done a lot of fixtures for, as I mentioned there in the little quick blurb. The thing is, when working with, I'm not going to say any names, of course, just keep it generic, but they're all still using drawings, all of them. So when is this MBD going to get to the big medical device manufacturers?
I have not a good answer for that. I think big companies, they're, of course, by their very nature are a lot slower to adapt. I would probably see, for product design, less emphasis on moving away from paper, or not paper, but 2D drawings, just because there's so much history and whatnot for them. But smaller companies and dealing with, in the prototype world, I see 2D drawings. That would be the first place where this starts.
Early adopters, right?
Yeah, it's going to be in there, and it already has. Like I said, when you send a model to be prototyped by we have proto labs here in Minnesota. They do prototype injection molding, and their website doesn't. You just load the SolidWorks model right directly onto their website, and then they come back and give you a injection molding quote from that. And there's that's just one of the companies that does that kind of thing. So
absolutely.
It's in terms of the bigger players, of course, it's going to take longer. But working with model shops and prototype houses, I see that it's already happened. So,
just to give people some insights, we have a lot of medical companies that we work with, but some of the bigger ones, we are in October 2021 now, so it's almost 2022. Some of the bigger ones are using SolidWorks 2019, and it's not because they don't have the budget to upgrade. It's like just moving things, upgrading. You have to do it across the whole company. So they're expected to be probably the last ones to adopt MBD. So let's talk about the efficiency aspect, like saving time. When you said that, it caught my attention, and probably a lot of our listeners. You said it's easier, it saves you time to do MBD. Could you give us like maybe an example? If you do a drawing, like an assembly drawing, a BOM, let's say it has 20 parts, 20 components in the BOM, how much less time are you saving using MBD? Where are the time savings coming from?
Yeah, I don't think the time in assemblies are pretty easy to document. So there's at least, you're basically taking something that's already done, and you're putting an exploded view, putting some balloons on it and creating a bomb. And so that's almost already kind of automated. I think the big savings comes in when you're detailing parts. And so you have this part, might be fairly complicated piece that, so you spend you've already gone through and created all the sketches that are being used to extrude and cut and rotate and whatever you needed to do to make the part in your CAD model. And I know hopefully people listening to this, if you're not familiar with CAD, I'm sorry, I don't know how to say it any.
No, this is for CAD people. Like this specific episode it's going to have SolidWorks in the title. Yeah.
Yeah, you've already done all that work to do that, and now you bring the part into your drawing, and now you do the whole thing again. It's like writing a book, and then going and writing the book again. There's no value added in doing that. So it's just busy work. And so that's where I think it saves time. And we've done something, we've instituted in our standards an ability to take a model, put it onto a drawing, put 3 datums on it so the part's fixed, and then just put a blanket profile tolerance over the whole thing. And then reference the model in the notes. And that basically does almost all of what MBD is supposed to do. You still have the drawing, so you still have the ability to review, and it doesn't upset your flow, your workflow. But you're not spending, you're spending very, very little amount of time on the actual drawing. So
can we put that into context? Compare it to how much it would take to do a parts drawing versus MBD. Are we talking only 10% of the time? How much?
It depends on the complexity of the part, but how long do you spend to do a drawing of an average part? Say it's something that's intended to hold an air cylinder. Say, so it's a plate with a bunch of holes and maybe some notches in it. So you go in and you bring it up, bring the view up, put your dimensions on it. And so all that time you're spending doing that, which you've already done once before when you created the part to begin with, now you instead of doing that, you bring the part up, you attach 3 datums to it, ABC, and then you put in the notes that all dimensions not called out here are shall abide by this profile tolerance, and with the datums as indicated. And that's it. You don't have to detail the part anymore.
Wow, this is wonderful. This is really wonderful.
And the standards, there's ANSI standard Y14.41, which is the kind of the digital product definition standard, details how, it says that you're allowed to do this. You're allowed to create, use the model and reference it in your drawing. And so that's kind of what we do now. I'd like to see us get away from the drawing entirely, but we do have a workflow that requires approvals, and like I said, we do have certain requirements that we're, in a medical device design situation, that require us to have something that we can review, and the drawing is an easy thing to review.
So Sean McGilligot, our previous podcast guest, had said that you were the chair of documentation standards work group, and you figure out how to document SolidWorks designs. Let's put that into context. Does that mean that other people are designing the parts, and then they send them to you, and you just do the MBD and the documentation, or you do both?
No, we have a group of us. I don't know. There's about 12 of us that do design, and we all do our own drawing, mostly. And then of that, there's a subset of machinists and designers, designers and engineers that we kind of get together. Whenever you have documentation, there's always some question or something that comes up that we don't know how to answer. It's not addressed by the standard. The fact that we can even use this electronic definition standard at all came out of that group. And we meet we were meeting quite frequently, but over the last few years, it's been less and less as less issues come up. But yeah, so we decide things like we're like the court of appeals for mechanical design at Mayo.
You mentioned about the pitfalls of specializing in one thing. Could you elaborate a little bit more on that?
Okay, I was just kind of talking about my personal attitude. So this is a different kind of changing gears a little bit.
Subject altogether, yeah. You're correct.
So I feel very fortunate that I work at a place where I can be doing, one day I'm working on a fixture to, patient immobilization fixture, which in order to hold somebody in the same position for some kind of a cancer treatment. And the next day I'm working on something that would hold a mouse in that particular location those are kind of the same thing, but they're very different. Or a surgical retractor, or some way to position so a patient can position their eye for a certain treatment, or something that would some other effect of a filter that would go into place in the treatment of cancer. So there's all these different things that we get to work on, and that I love that. That's what I really like about engineering, that I'm not doing the same thing. But when you go through school, and it's even getting worse, even at high school levels, kids are being told to specialize in something, and then you get to college and you specialize in engineering, and even in engineering you specialize in mechanical engineering, then in mechanical you specialize in fluids or materials or whatever, and you're going through this progression of specialization until you get out. You might even go and get a master's degree, and that's even more specialized in one particular subject, and then you work in that particular thing your whole life. And I consider myself a jack of all trades but master of none. And people say, "Why do you say that? That's like a criticism. You're not good at anything or any one thing." And I say, no, I'm okay at a lot of things, but I'm not really, really good at any one thing. And I think that's like, if I was to describe myself in one sentence, that would be it. That I'm not I don't know how many positions there are in the world for engineers that are like me, but again, I feel very fortunate that I found this one. And I think in the way we work today, we can switch gears, midstream, and do. I encourage people to do and try a lot of things, a lot of different things.
I appreciate you being so modest when you say that you're okay at a lot of things. Obviously, if you're working at Mayo Clinic, you're cream of the crop. You're probably the best at a lot of things, but you're just saying you're okay. But I was going to ask you, what are some of those things that you do that you're okay at?
Well, so a lot of times we have to we have to write code. Say I'm making a device that's intended to dry blood spots. The patients we prick people's fingers and we put the blood onto a piece of paper that creates a blood spot, and then we hang them out to dry. Well, I had a project where we were asked to make a dryer for, this is done it's done on adults, but it's primarily done on babies. They prick their feet and to get a blood sample, and they put it onto a card, and then they hang it up on a clothesline to dry. And so we had to invent or come up with a dryer that would dry the blood spots and control the temperature. So to control the temperature, we had to write some code, and I had to write LabVIEW program that controlled the temperature of the dryer, stuff like that. So you learn how to write LabVIEW code, and that was very exciting for me to do that, even though I could have probably offloaded it to a programmer who knew better. I liked doing that, so I did it. I might one day be in the machine shop and want to cut something with the lathe, so I asked the machinist, teach me how to use the lathe so I can just make stuff on the lathe. And so I'm making stuff on the lathe, and that's not necessarily engineering, but it's important to get that knowledge of how things are done. One day I'm working on a fluids problem using some computational fluid dynamics analysis. One day I'm working on a finite element model of a mechanical structure. One day I'm just doing straight up, mechanism design. So there's just a whole host of things that you can do. But if you specialize just in, I'm just going to do computational fluid dynamics, then you'll be really good at it. You'll be way better than I could ever be at it. But you're missing out on the mechanism design or some other.
Let's talk about that. Stuff. Let's talk about that mechanism design. I actually have I post a video a month of a product that I tear apart. It could be anything. One of the most popular ones that I've done here at Pipeline and with SolidWorks. They're sponsored by SolidWorks. So I'm very fortunate to do a hobby that's also sponsored. So I tore apart a handle from my luggage, and this is actually the idea from Aaron Moncur, the founder of Pipeline. I taught people the mechanism on YouTube. So if anyone listening to this gets on YouTube and you type in SolidWorks luggage handle, you'll see the video that I made that has over 10,000 views and over 100 likes and like 1 dislike. So everybody loves the video basically. And I just really like learning mechanisms, how they work internally. It's like fascinating. So any advice for someone like me that wants to get better at mechanisms?
Well, you're doing it. Taking stuff apart is the best thing, or just looking at things and saying, well, how does this work? That's something I think that is something that I've been doing my whole life. Don't be afraid to take something apart. I'm not recommending people go out in their garage and start taking their cars apart, but don't be afraid to do the.
Can't go to work the next day.
If you're, I do these. One of your guests was he made videos, like instructional videos, and I thought, wow, I've always wanted to do that. I've tried to do that. I'm not very good at it.
Jono, I think that was his name. Yeah,
he had. So he's got some really good videos of how to, and your experience with doing videos. It's like I take things like I'm, in my house, I made a video of taking apart my faucet and how does that work, and taking apart. I have a Mini Cooper, and I had to replace the clutch, and so that whole thing was quite a, I wasn't, but just to not be afraid to do things like that, because that's how you learn. As far as mechanism design, though, that's where SolidWorks is really good. Just being able to model CAD mechanisms, assemblies, and by controlling the constraints, you can rotate things, and there's even the availability of motor features and things like that allow you to actually simulate the motion.
The one thing that I'm not sure if we were the originators, but it was certainly our original idea that we had here internally at Pipeline, we came up with this called a mental mechanism library, which we suspect that mechanical engineers and people that do mechanical mechanism design, they have this mental library of things that they've seen across their lifetime that they probably haven't written down, but they just have it stored in the back of their mind. And when they're faced with a problem, they pull from this mental mechanism library, and that's how they can solve the problems. Would you agree on that?
I would totally agree with that. I think that's, you talk about reverse engineering and all that. I think almost all I shouldn't say this, but I copy a lot of things from the world, that, you chances are somebody's already done what you're thinking of doing when it comes to this kind of stuff. So, and then I have a book. It's an old book I found. I actually found it at Mayo, on a shelf of a guy that had retired, and it was a book of mechanisms, and it just had all kinds of mechanisms in it. One of my favorites is a Geneva mechanism that you take a constantly rotating thing and you convert it into a discrete, incremental motion of movement. It's what's used in what makes a second hand click in 1 second intervals and not just move smoothly.
I'm looking at it right now in Google Images.
Yeah, Geneva mechanism. Yeah, so those kinds of things, and how to take a crankshaft as turn rotational motion into linear motion. How the hand works in terms of opening and closing things. I do that a lot when I'm working with doing surgical instruments. Those things. We created a generic handle that we can apply to any number of, looks kind of like a scissor handle or a hemostat handle. How that size for different size surgeons, and it's kind of off topic, but we're getting a lot more women are becoming surgeons than in the past, and so the surgical instruments are designed for men, and they're typically bigger, and we've gone in and done basically reverse engineered various pieces of equipment to make them smaller for a woman's hand, and so that kind of stuff is super rewarding. Wonderful.
Is there anything else that you'd like to share with the viewers? Anything that I haven't asked you that I should have?
One thing I was going to say, though, in terms of you guys at Pipeline are fairly similar to how we operate. Kind of I'm sure you have projects and they're fairly unique. You're not just making catheters or some other thing, but you're doing various different pieces of equipment but you're the difference is we're doing stuff at the front end for the design, working with surgeons and clinicians in the hospital and creating that part of it. And then you guys are taking whatever the devices are that need to be made and creating, supporting the creation of those devices in production. And so I think that's kind of interesting.
Well, thank you for that. And thank you for looking into what Pipeline does at teampipeline.us. I really appreciate it. This was Steve Corner, the principal engineer at Mayo Clinic, and it was a joy and a treat having you on the podcast, Steve.
Oh, thank you for having me.
I'm Aaron Moncur, founder of Pipeline Design and Engineering. If you liked what you heard today, please share the episode. To learn how your team can leverage our team's expertise developing turnkey equipment, custom fixtures, and automated machines, and with product design, visit us at teampipeline.us. Thanks for listening.
Dear valued listener, we kindly ask that you help us get to 100 5-star podcast reviews in the platform of your choice. For a chance to win a $50 Amazon gift card, send a screenshot of your 5-star podcast review to podcast@teampipeline.us. You'll find that email address in the description of the show notes.